Good morning, everyone. Today I'm going to present to you a work entitled Nonlinear Optimization over the integer efficient set of multi-objective integer linear fractional programs. First, I will give a brief presentation of the multi-objective problem and the optimization over the efficient set. Then I will define our problem and I will present the proposed method to solve it. Afterwards, I will end with a numerical example and conclusion. So, let us concentrate on multi-objective problems. The multi-objective optimization problem defined on the set X of feasible solution consists in maximizing or minimizing r conflicting function simultaneously. R is greater than or equal to 2 and X is implicitly described by constraints of equality and inequality. The set which contains X is called decision space. The set which contains Fx is called objective space. The set F is the projection of X on the objective space. Among the particular cases of the multi-objective problems most encountered in the literature, we see the linear multi-objective problem, called MOLP, where all the functions are linear. The multi-objective integer linear problem, called MOILP, in which the feasible solutions are integer, and the multi-objective integer linear fractional problem, called MOILFP, where all functions are linear fractional and the set of feasible solutions is discrete. Now we define the two concepts, dominance and efficiency. Let F1 and F2 in objective space. We say that F1 largely dominates F2 if and only if F1 is at least as good as F2 on each of the criteria. We say that F1 dominates F2 if and only if F1 is at least as good as F2 on each of the criteria, and F1 is different from F2. And we say that F1 strictly dominates F2 if and only if F1 is strictly greater than F2 of each of the criteria. A non-dominated set, noted S and D, is the set of all points Y in objective space F such that Y is not dominated. What does it mean to solve a multi-objective problem? It is to determine the non-dominated set and provide for each point the solution X which corresponds to it. These solutions are called efficient solutions. The main difficulty that can be encountered when we attack this problem is that the non-dominated set is very large and even infinite in the continuous case. So it will be impossible to provide a polynomial algorithm given that the output itself is exponential. Despite this difficulty, there are many methods to solve small-scale and medium-scale size instances. I cite here some works dealing with the problems of multi-objective optimizations in the linear, nonlinear, continuous, or discrete case. Enumeration of all efficient solutions of the multi-objective problem is not always recommended because it may turn out that this efficient set is very large and it becomes impossible for the decision maker to choose the best compromise in terms of his preferences. The optimization of a criterion which expresses the preferences of the decision maker over the efficient set constitute therefore an essential research subject this field. A most preferred efficient point which maximizes the fractional utility function of decision maker can be obtained by solving the following problem. Minimize or maximize a function f such that x belongs to the set of efficient solutions denoted by xe of the multi-objective problem defined previously. This type of problem was first studied in the continuous case, and since several researchers, motivated by many applications have been interested in the optimization of a function over the efficient set of a linear multi-objective problem. Unlike the continuous case, which has been extensively studied by many authors, the discrete case did not see as much of a similar development, and here is a bibliography concerning this type of problem. In this context, we present an exact new method which maximizes a linear fractional function over the efficient set of a linear multi-objective integer fractional problem, avoiding systematic passage of the whole set of efficient solutions. The problem can be formulated as follows: maximizing a fractional function f, and x belongs to the set of efficient solutions of the MOILFP problem, which consists in maximizing on the set x of realizable integer solution R linear fractional functions. This problem is in principle very difficult to solve. This is mainly due to the non-convexity of its achievable set, the nature of decision variables which are integer. Add to that the implicit form of the main criterion, which is non-linear. As an application of our method, we can considering an optimization problem of a linear fractional utility function of decision maker over the integer efficient set of a multi-objective linear fractional transportation problem, MOLFTP, introduced by Sophia and al. Then the mathematical model of MOLFTP can be formulated as follows: minimize R function zk, k ranging from 1 to R, writing as a double sum of CEG XEG plus lambda e, divide by a double sum of DEG XEG plus gamma e, under constraints sum XEG G ranging from 1 to n equal to AE, and sum XEG E ranging from 1 to m equal to BG, and XEG are integer variable. AE is the supply available at the source E, and BG is the requirement at the destination G that satisfy sum AE equal to sum BG. Here CEG and DEG are respectively the actual unit cost and the standard unit cost of transporting from source E to destination G. In order to achieve maximum transport profitability, which is an index of operational efficiency of the firm defined by the ratio between the present value of a project and the required investment made, it is expressed as a linear fractional function, where PEG are value of the project from E to G, QEG are value of the required investment made from E to G, and alpha beta are fixed value. Now we present a method to solve the problem. This method is iterative, where in each iteration the feasible domain is reduced and allows to find the optimal solution without explicitly enumerating all efficient solutions of the problem. Let the LFP over efficient set of the MOILFP problem. The proposed method consists of solving at each iteration a relaxed problem RL by using any mixed integer linear fractional programming method, where RL is defined as follows: maximize a function fx such that x in DL, where DL represents the set of feasible solutions at step L. L is the number of the current iteration. The steps of the method are summarized in the following algorithm. As output, we have the optimal solution x-opt and its associated value f-opt. We initialize L equal to 0. D0 is the feasible set of multi-objective problem. X0 is the empty set. F-opt equal to minus infinite and F sub equal to infinite. While termination condition is not met, do solve RL problem with any linear integer fractional programming method. If RL is unfeasible, then the main problem LFP over MOI LFP is also unfeasible. Else, RL has an optimal solution X star L. We set F sub equal to Fx star L, an upper bound for the value of F. Here we test if sub greater than F-opt. If yes, we test the efficiency of X star L. Else, we stop and return F-opt and X-opt. The efficiency test of a feasible solution X star of MOI LFP can be verified by solving the mixed integer linear program TF as proposed in saying and all. We have to maximize in the set of feasible solution D the sum of the positive variable psi such that CE minus ZE x star DE x minus psi equal to ZE x star gamma E minus lambda E for each criterion E, where ZE x star equal to CE x star plus lambda E divided by DE x star plus gamma E. A feasible solution X star is efficient if and only if the optimal value of the problem TF X star is 0. And for t equal to 0, we solve the problem TF for the solution xt. If the optimal value is not 0, then xt is not efficient. In this case, let t equal to t plus 1 and solve tf xt until an efficient solution is found. The sequence xt certainly converges to an efficient feasible solution of the multi-objective problem. Now, if x star L is efficient, then we update x-opt and f-opt, and the algorithm stops. Else, let x hat L, the efficient solution, returned by efficiency test and by using theorem 2. We may have an equivalent solution to x hat L that doesn't necessarily have the same value of f. Therefore, we solve the following problem. Tx hat L, which maximizes the function f such that x in D, and for each criterion E, Ze equal to Ze at the solution x hat L. Now, let x bar L be an alternative solution. If f-opt less than or equal to f bar L, then we update f-opt and x-opt. F-opt equal to f x bar L and x-opt equal to x bar L. And construct the domain DL plus 1. We add the cuts to reduce the set DL. The first one, ZEX greater than ZE at X bar L for at least in one criterion. This constraint can be written in different form, where epsilon E the minimal increment of ZE and minus ME represent the lower bound of ZE, YEL in 0, 1, and if YEL equal to 1, then a strict improvement over the criterion ZE is forced. And we must have the sum of YEL ranging from 1 to L is greater than or equal to 1. After developing equation 4, it can be written as follows. This constraint is not linear due to the term DEYELX. However, since YEL in 0, 1, we can transform it to a linear constraint by introducing a new variable WEL equal to DEX YEL. Then we have WEL is equal to DEX if YEL equal to 1 and 0 otherwise. Consequently, the new domain of iteration L plus 1 is defined as the following, where the first constraint represents the equation 4. The second and the third one represent the condition relating to the variable YEL. And we add the inequality WEL less than or equal to DEX, WEL less than or equal to YEL UE, and WEL greater than or equal to DEX minus 1 minus YEL UE. Here UE is the upper bound of ZE. After the construction of the new domain, we set L equal to L plus 1. Now, to illustrate how this algorithm works, we consider, for instance, the following problem. Max fx equal to 4x1 plus x2 minus 2 divided by 2x1 plus 3x2 plus 1. And the constraint x is efficient solution. For the problem, max z equal to minus 4x1 plus 3x2 minus 3 divided by 2x1 plus x2 plus 2. And the second objective is x1 plus 2x2 plus 1 divided by x1 plus 3x2 plus 1. And we have the constraints minus x1 plus x2 less than or equal to 0, 2x1 plus 3x2 less or equal to 11, and x1 greater than or equal to 1. x1, x2 positive and integers. We start by initializing L to 0, f sub to plus infinite, and f opt to minus infinite, and d0 to d, the set of the feasible integer solution. First, we solve R0, consisting to maximize the function f equal to 4x1 plus x2 minus 2 divided by 2x1 plus 3x2 plus 1, and x is defined by the inequality of the MOEIFP problem, which are minus x1 plus x2 less or equal to 0, 2x1 plus 3x2 less or equal to 11, and x1 greater than or equal to 1, x1, x2 in n. The resolution of the problem R0 led to the solution x star 0 equal to 5, 0, and fx star 0 equal to 18 elevenths. F sub is then 18 elevenths. We test the efficiency of the solution x star 0 using the program tfx star 0. The solution is not efficient, and the program returns an efficient solution x hat 0 equal to 1, 0. In the upcoming step, we search for another alternative efficient solution with a better outcome of f by solving the following program. Here minus 7 quarters and 1 are the value of z1 and z2 at the point 1, 0. The optimal solution is x hat 0 equal to 1, 0. That means that no alternative solution is found. And as f opt is less than f x hat 0, which is equal to 2 divided by 3, we set f opt equal to f x hat 0 and x opt equal to 1, 0. Now we construct the set D1 as we have shown previously. We give for this example M1 equal to 6 and M2 is 10, U is equal to 110 and 88, and epsilon equal to 0.1 and 0.1. D1 is then the following set, and we set L equal to L plus 1. The obtained domain D1 using the construction given above is given in the following figure. Here delta 1 represents the first constraint in the case where y1 is equal to 1. That means that the first objective must be improved, and delta 2 represents the second constraint in the case where y21 equal to 1. That means that the second objective must be improved. If y21 equal to 1, then the domain becomes infeasible. Therefore, one can notice that the figure shows only the reduced domain in the case where y11 equal to 1. Solving the relaxed problem on the set of feasible solution D1 gives the optimal solution for 1 with the value equal to 1.25. We set f sub equal to 1.25, and as f sub greater than f opt, we test the efficiency of the solution x1. x1 is efficient. Then we update the value of x opt and f opt. X opt equal to 4,1 and f opt equal to 5 divided by 4, and the algorithm stops. As conclusion, we can say that the method presented here consists to reduce the set of feasible solutions at each step of the algorithm by introduced cuts. In the computational study, the method allows to solve small scale size instances and as well as the medium scale size instances. Moreover, the study can be extended for other preference functions where the suggested method can usually be adapted to solve the problem of optimizing of a convex utility function over the efficient set of MOILFP. However, the proposed method gradually add disjunctive constraints which significantly reduce the efficiency of the suggested approach. We gave some bibliography, and thank you.